Here we're going to move into working with regression equations. Now, once you've conducted your correlation hypothesis testing and you're certain that there is indeed a relationship between these two variables, the next thing you want to do is calculate out what is the nature of that relationship numerically that would allow us to then make future predictions. So the equation is of the straight line that's going to best fit a scatter plot of the sample data. So this best fitting straight line is called the regression line. So that's the line that's actually plotted on the graph. And the equation that produces that regression line is called the regression equation. Now, why all of this matters? Because what we want to do is we want to be able to make better predictions about the future. This is one of the primary goals of stats, is to be able to make predictions based on current data about possible future outcomes. And the better we are at predicting the future, the more likely we are to succeed. And this is true in terms of a business making money. This is also true in terms of individuals, for example, trying to stabilize or increase the biodiversity in environmental areas. So whether you're looking at a population growth in terms of animals or species diversification, if we're looking at a business, if we're looking at what we can do to help individuals who are dealing with cancer have better outcomes, all of these things are outcomes that we would predict with regression equations and try to be able to hone in on what can make a difference. And then that, of course, is where you focus your intervention. So we use the regression equation to make predictions for the value of one variable, i.e. our outcome of y, when we're given a specific value for the other variable, and in this case, it would be x. So regression equations are really useful because they help us predict the future, and the better our regression lines, the better our predictions for the future, in terms of them being more accurate. So we have a requirement check we have to run for using the regression line, and in fact, it's exactly the same thing that we do for a correlation. So here we have we need to have our simple random sample of quantitative data. We need to have no missing data. So of course we've got to have paired data for each individual. Again, outliers, just like they were a real problem with correlations, they're also a real problem here with regression lines. They can really draw off your regression line. So all those factors that we looked at with correlations in terms of clustering data or outliers, all of those same outcomes apply to regression lines, okay? And it has to be linear because, again, we're doing a formula for a straight line. So one of the things you want to keep in mind is deciding on your best strategy for predicting the value of y, because, again, this is the overall end goal when we use a regression line. We want to be able to get the best prediction for the value of y for a given x. Now, this flow chart here comes from your textbook. So it's figure 10.5 in your textbook, and I strongly suggest that you make a copy of that and put it into your notes. So the first thing we need when we have this, we need to be asking ourselves, is the regression equation a good model? Is it going to work or not? We have a regression equation. This is true. Is it actually going to be a good model or not? So there's three things we can look at. So we look at the regression line graphed on the scatter plot, shows that the line fits the points well. So we've got our raw data. We can look at our regression line as it graphs onto the scatter plot. We can look at our R. So if we're working with something where for whatever reason we don't have the raw data, we're just given the R, we can use that as an indication of a linear correlation. And we also need to pay attention of whether or not the prediction is too far beyond the scope of the available sample data. So remember, when we're doing a regression line, we're predicting it with the current set of data. It's a linear relationship. But do keep in mind, relationships can plateau out at certain high levels or certain low levels. And in fact, in some instances, can even actually go the other way. They produce a curvilinear relationship. So if we're trying to make predictions too far away from our available sample data, we're moving into an area that could or could not be part of a curvilinear relationship where the shape of the relationship changes. So we want to keep pretty close to our available sample data. So if we're looking at this and we meet these criteria, then we can say, yes, the regression equation is a good model, right? And in that case, we're going to use the formula here that we can see at the bottom left-hand side when you're looking at it. So it's the y-hat formula. So that is for predicting a particular value of y given a value of x using a regression equation. It's our y-hat. If, however, we don't meet these criteria, then the answer is that the regression equation is not a good model. It's clearly often not doing a very good job of predicting. So that means that regardless of what the value of x is, then our best predicted value of y is going to be the mean of y. So before you move in, as soon as you get a regression equation, don't immediately start going through and processing for your value of x for your y. You need to check and make sure that your problem meets these criteria before you move forward. Okay, now let's take a moment and look at the components of a regression equation. Now, you're not going to calculate these by hand, but I do want you to have some familiarity and understanding of how these formulas work. So for here we have B1, which is our formula for the slope. Now notice that when we go through and we do our formula for the slope, notice that both of those are using the standard deviation values. So we use the standard deviation of the y values and the standard deviation of the x values and part of our calculation of the slope, and slope being the degree of angle of the line for the linear relationship. Now the other part of a regression equation is the y-intercept. Where would this line come across the y-bar? So keep in mind your x's are always going to go along the bottom line and your y always comes up. Okay, so you're always going to have, your x is always going to be the horizontal line and your y is always going to be your vertical line. And here we can see when we're looking at the formula for the y-intercept, we're using the mean of the two values. So we use our mean of y and our mean of x. So the intercept is based off of the means of the two samples, of the two measurements, and then the formula for our slope is based off the standard deviation of those two measurements. Okay, so let's take a look at using a regression equation. So we're going to do problem number 5. It's on page 514. So here we've got an R of 0.687, and we're given a regression equation of 47.4 plus 0.18 times x. So we need to ask ourselves, does this regression equation appear to be a good model? And again, you're going to go back and look at that flow chart that we just used. So looking at that flow chart, we know we don't have access to the raw data here, so we're going to be taking a look at the R value. So take a look at that R value. Does that tell us that this looks like it's going to be a good relationship to rely upon for this particular problem? Pause the video, go back and look at that flow chart, make your decision yourself, because you need to be doing this now, practicing in these PowerPoints to be able to do it correctly on the exam. Yes, it would indicate, so we've got 0.687, this indicates a moderate to strong relationship. So we have a good reason to feel that this is probably going to be a useful equation for us. Now, let's take a look at the components of this regression line. Let's break this down and look at how we talked about there's the y-intercept and we talked about there being the slope as the two values. So let's take a look at where these look like and match together with this particular equation. So our y-intercept is going to be the first number in the equation. All right, so always in your regression equation, the first number is your y-intercept. In this case, it's 47.4. And then following that, there's going to be, we always have an addition sign, and then we have our value for the slope. Now, the value for the slope itself can be positive or negative, but the symbol between the two is always going to be an addition sign. So here we see our slope is 0.18, and we're going to times that, multiply that by our x. So we would take a given value of x, plug it into this formula to predict what the value of y would be for that x. Now, just to take a really quick look at how these match up, notice that our larger equation we were looking at before, we were calculating with our standard deviations of x and y and putting them together for calculating the B1, and B1 stands for your slope. So B1 is your slope, and then we can see B0 down here is your y-intercept value. So you can see, although we're not using these large formulas, I want you to see briefly how they match in to calculating what our slope is going to be and also then what is our y-intercept going to be. Okay, so the next step we need to do in solving this problem is we need to label our variables and set the measurements, because keep in mind when we're looking at these correlations, these do have associated measurements, and that makes a really big difference. So you want to make sure that you're labeling your factors and your variables and make sure that you're specifying their level of measurement. So here we've got x is the duration in seconds, right? So how long the eruption goes on. And y is our interval in minutes, how the space in between the eruptions. So now we want to ask ourselves, what's the best predicted interval time following an eruption with a duration of 120 seconds? So we've timed this most recent eruption was 120 seconds, and we want to make a prediction. Somebody goes, how long do you think it's going to be before it erupts again? And you want to be able to give them an estimate. So what we're going to want to do in order to answer that question, since we've already decided this is a good regression model, is we're going to take our 120 and we're going to be plugging that into our equation. So we've got 47.4 plus 0.18, and we're going to times it by our new value of our new value of x, 120. Okay, so we plug in our 120, and when we run that equation, we get 69 minutes. So we would have reason to estimate that it would be 69 minutes before the next eruption. Okay, so now we've done that one. Let's go and take a look at another sample problem, and I want you all to work through this one on your own, and then we'll check your work as we go along. So here we've got, again, we're looking at Old Faithful here, so we've got our geyser that's going up, and we're given here for problem number 6 on page 514, we're given an R of 0.0915. Okay, so we have that set up, and then we're given a Y. We're told that our equation is 119 plus 0.033 times X. Okay, so there's our correlation, and there is our regression equation. And we're given that our X bar, our mean of X, is 245 seconds, and our mean of y is 127.2 feet. So we want to ask ourselves, what is the best predicted height of an eruption with a duration of 120 seconds? So the first thing we need to ask ourselves, of course, is does the regression equation appear to be a good model? Again, going back and looking at that flow chart that we have, does this appear to be a good model for making our prediction? So pause the video for a moment, go take a look at that and make your decision, and then come back and we'll check your work. No, it does not. 0.09 is a non-existent relationship, which would indicate that this is not going to be, using the regression equation is not going to be our best option for this. So what are we going to want to do? What's our next step looking at that flow chart? What do we want to do to give a prediction for y? So we've got to do, we have an eruption with a duration of 120 seconds. They say we want you to make a prediction about how high it's going to be the next time. Okay, your regression equation doesn't work, but you still need to make a prediction. So what are you going to use? We're going to use your mean of y. So we're going to say, okay, well, my best guess at this point is it's going to be 127.2 feet. So, wrapping up this first set of the lectures on regression equations, be really careful about using your flow chart. That's going to be super important in deciding whether or not you should use your regression equation or whether you should use your mean of y. Okay, and be clear about how you're going to take a given x value and plug it into your regression equation to get a calculated corresponding y value. Okay, the next lecture is going to look at a couple more examples of working with regression equations.